Today we are going to see about angular velocity and its relation with linear velocity. So in rotational motion of a rigid body about a fixed axis, every particle of the body moves in a circle. So now this is a rigid body. It has n number of particles. So we are considering one particle. This particle rotates about the center C, and this is the axis. Okay, fixed axis. Now we have this as the radius of the circle, and it goes with the velocity, linear velocity v, and the whole body will have a angular velocity. So now what happens is, we are considering the point P, particle P at point P, and after some time, say del t, after some time, say del t, very small time, because of the rotational motion, now in this case it is moving anti-clockwise. Because of the rotational motion, this particle has moved from this point to this point, making an angle del theta, very small angle. So because of small time, it makes an angle del theta. Now we have to find the average angular velocity, which is nothing but del theta by del t. Del theta, del t is the time taken for the particle to move from this point to this point. It takes this much time, del t. Now when this del theta tends to 0 or del t tends to 0, so del t tends to 0, that means a very negligible time. Del t tends to 0. The instantaneous angular velocity, which is omega, okay, which is equal to d theta by dt, rate of change of this angle theta. Okay, now this is the relation between omega, which is instantaneous angular velocity, in terms of theta and time, that is rate of change of theta with respect to time. So now we have interested to find a relation between linear velocity and angular velocity. So the formula for linear velocity and angular velocity is v is equal to omega r. Since all the particles move with the same angular velocity, it can be written as v is equal to omega r. So this term will not change. Whereas particle at different radius, say suppose if you are interested in a particle here, so this will be having a radius other say r1, and this will make a velocity of v1. That is, v1 for this particle is equal to omega into r1. So velocity at this point, linear velocity at this point, having a radius r1 about the fixed axis. So the v1 is equal to omega into r1. Now if you carefully note, this omega is not changing. Why it is not changing? Because all the particles moves with the same angular velocity. Similarly, if you consider another point, say this point, which is having a radius r2, and this is the circular path, and this is the linear velocity v2. So the connectivity between linear velocity and omega is v2 is equal to omega r2. So here again omega is fixed because all the particles in this rigid body will move at the same angular velocity. Whereas if you check out for a linear velocity depends upon the radius. Now what happens is, if r tends to 0, this radius is 0, means it falls on the axis, z-axis. So in that case, there is no linear velocity, it is 0. So if this r value tends to 0, that means if the point lies exactly on the axis itself, then the velocity, linear velocity is 0. So this is the point you have to remember. So the formula you have to remember is, for average angular velocity, del theta by del t. For instantaneous angular velocity, this del theta or del t tends to 0. So therefore we have omega is equal to d theta by dt. And the relation between linear velocity and angular velocity is v is equal to omega r. Now for different particles at different radiuses, we have the relation v1 is equal to omega r1, v2 is equal to omega r3, v3 is equal to omega r3, likewise it keeps on going. That means the velocity of the individual particle in a solid rigid body depends on the radius from the axis of rotation. This you have to keep in mind. Okay. Now, so that's what is explained in this diagram also. We have separated that portion alone. So this is the center of this circle. This is the point P, and the axis of rotation is this. And this r vector is nothing but a position vector to represent this point. Otherwise, the general connectivity between linear velocity and angular velocity is equal to v is equal to omega cross product with r. So now this is a vector product, cross product. So now omega cross product with r. Now here if r is like this, omega is like this. Now omega cross r, that means if you extend this line straight away, this r perpendicular or radius of this circle is in this direction. Okay. Now what happens is omega cross product means this omega is eating like this. So it moves in this way clockwise. Therefore the movement, the resultant velocity will be perpendicular to both omega and r. So that is omega hitting r, omega cross product with r vector. So then when it hits, it is moving this way. So the resultant linear velocity will be perpendicular to like this. Okay, that is omega is like this, r is like this, and omega is in this direction, r in this direction. The resultant linear velocity will be in this direction. So what I try to say is the linear velocity is basically a vector in which we can represent angular velocity and radius of the circle as a cross product, vector cross product. So linear velocity v vector is equal to omega vector cross product with r vector. That's all about angular velocity and its relation with linear velocity. We have seen two cases, the general formula and linear velocity, expressing linear velocity as a cross product of omega and r. Hope you have understood this topic on angular velocity and its relation with linear velocity. Thanks for watching. Nandri.